Hey, welcome. Have you ever wondered how we measure things that seem, well, impossible to measure? Like the area of a field with a really weird, curvy border. Well, today, we are going to pull back the curtain on a super powerful math shortcut that turns the impossible into the good enough. Let's get right into it. So, picture this. You've got a piece of land. One side is a perfectly straight road, but the other side is a winding, twisting river. How in the world do you calculate its exact area? Now, this is exactly the kind of problem that calculus was invented to solve. But, sometimes even calculus needs a little help. Because, let's be real, in the real world, that river's curve doesn't follow some nice, neat little formula we can just plug in. Finding that perfect exact area, it can be incredibly hard, maybe even totally impossible. And that's exactly why we need a clever shortcut. And that workaround, it's got a name, numerical integration. Now, the most important word on this slide is right there in the middle, approximation. We're not trying to get the one single, absolutely perfect answer. We're looking for an answer that is good enough to be incredibly useful. One of our sources really puts it perfectly. The whole point is to work from a set of numerical values. This is math that was designed for the messy, complicated real world, not just for the clean pages of a textbook. And this isn't just a niche problem, this pops up everywhere. Maybe the formula for our curve is just a complete mathematical nightmare, or, and this is way more common, maybe we don't even have a formula to begin with. All we have is a bunch of data points, a series of measurements from the real world. What do you do then? Well, here is the absolutely brilliant idea. If the whole problem is just too big and too hard, why not break it down? Let's just slice it up into smaller, simpler pieces. We can take that whole complicated area under our weird curve and just chop it up. Imagine a bunch of really thin vertical strips. See? Each one of those little strips is way, way simpler to deal with than the whole big curvy shape. Okay, and here's the real magic trick. For each one of these slices, just forget about the tricky curve at the top. All you do is connect the two top corners with a single straight line. And what do you get? A trapezoid. Just a simple trapezoid, a shape we all learned how to measure way back in grade school. It's that simple. So we've got this awesome visual idea, right? Just add up a bunch of easy-to-measure trapezoids to get a pretty good estimate of the whole area. Now let's take that simple concept and turn it into a powerful, repeatable formula. And here it is, folks, the trapezoidal rule. It's really just a systematic, organized way of adding up the areas of all those little trapezoids we just drew. It's a really elegant tool for getting a fantastic estimate. And you know what? The formula itself is surprisingly simple. First, you just figure out how wide each of your slices is. Easy enough. Next, you take the heights at the very beginning and the very end and add them together. Then you add up all the heights that are in the middle, and you double that number. And for the last step, you just combine those two sums and multiply the whole thing by half the slice width. That's it. Simple steps for a really powerful result. All right, theory is one thing, but let's actually see how this works with a real example. It's time to put this rule to the test and calculate something. Okay, here's our challenge. We need to find the approximate area under this particular curve between x equals 0 and x equals 6. And to do it, we're going to slice this area into 6 equal pieces. So first things first, we need to calculate the height of our curve at each point. Since we're making 6 slices from x equals 0 to x equals 6, the width of each slice, that h value, is just 1. In this table, this shows us the heights, the y values at each of those points. These numbers are basically the sides of our 6 trapezoids. And now we just plug our numbers into that simple 4-step recipe. Okay, so we take the first and last heights, then we add up all the ones in the middle and double them, we combine everything and then multiply by half. Let's see what we get. Boom, our result is 1.4108. So we've got our approximation. But the real question is, how good is it? Is it close? Okay, this is the moment of truth. We chose to go with an approximation instead of chasing perfection. So let's see how that choice actually paid off. Let's compare our result to the exact mathematically perfect answer. Would you look at that? Our result, 1.4108, is so incredibly close to the exact value of 1.4056. I mean, that's the real power of a good enough answer. It gets us almost all the way there with just a tiny fraction of the effort. Pretty cool, right? The difference, what we call the error, is just a little over 5 thousandths. For most real-world applications in engineering, physics, or data science, an error that tiny is more than acceptable. It's a fantastic trade-off. And that's really the heart of why this matters so much. The trapezoidal rule lets us solve problems where all we have is a set of measurements, not some clean, perfect formula. It's a true cornerstone of practical calculation, and it lets us turn messy, real-world data into answers we can actually use. So this whole idea of good enough is really the engine behind so much of modern science and engineering. It gives us answers to questions that seem flat out impossible. But it does leave us with a really fascinating final thought. When is good enough math not good enough? What are those situations where we absolutely positively need perfection?